In the previous module, we have seen that data can be non-normal and forceful assumption of normality can give misleading results. So, we use an alternative procedure to analyze such data, and this alternative is known as non-parametric procedure. In this module, we shall discuss functionals, linear functionals and nonlinear functionals, and lastly, we shall explain the concept of a plug-in estimator in the context of non-parametric inference. Before we go to details of this module, we start with defining some basics. Suppose x1, x2, xn is the data in hand. We assume that the underlying distributions are unspecified, but observations are independent. Therefore, the joint distribution of data is nothing but the product of the individual marginal distributions. Suppose the data is x and f, that is capital F, is the corresponding unspecified joint distribution. Then the pair x and f generates the induced probability space with elements sample space, the sigma field generated by the all possible subsets, and a probability, that is induced probability measure. So, we first explain the notion of an induced probability space. The term induced usually refers to a real valued function defined on a probability space. The real valued function then induces a probability distribution, whereas the original probability space may be different. In any inferential problem, our interest lies in knowing functions of the induced probability space. Now, for further development, assume that Px is the generalized density of data. That is, Px may be a probability mass function or a probability density function. In any situation, Px is either partially or completely unknown. In statistical inference, we try to give some idea about Px or some suitable function or functional of Px. Depending on the amount of knowledge of Px, inferential setups are either parametric or non-parametric or semi-parametric. So, the natural question is, how do we distinguish different inferential setups? We discuss one by one. First of all, assume that Px is partially known. Then we can write Px as Px theta, where theta is some unknown quantity. Now, theta may be numerical or abstract valued and is often called a leveling parameter. P is functionally known and omega is the set of all possible values of theta. So, when the setup is parametric, if theta is real or vector valued, the setup is parametric. For an example, consider IID observations xi from a Bernoulli distribution with mean pi. Then theta, the unknown quantity here, is pi and is real valued. The joint distribution, that is Px theta, is nothing but the product of each individual PMF. Thus, omega is a subset of the real line and hence the setup is parametric. Now, consider another example where xi are IID observations from a normal distribution with unknown mean mu and unknown variance sigma square. Then theta equal to mu and sigma is unknown but vector valued, and the joint density, that is the product of individual normal density, is a known functional form. Therefore, omega is a subset of R square and it is a parametric setup. So the natural question is, what is a semi-parametric setup? If theta is partly real or vector valued and partly abstract valued, the setup is semi-parametric. Let us consider an example. Suppose xi are IID observations from a mixture density, that is 50-50 mixture of normal and an unknown density. So px theta, the joint density function, is partly known and partly unknown. Here theta, the unknown quantity, contains mu and g. Therefore theta is partly abstract valued and partly real valued. Let us consider another useful example. Consider the linear regression setup with one non-stochastic covariate. Suppose xi are independent observations from the continuous density fi, where I runs from 1 up to small n, with expected value alpha plus beta into zi, where zi are known quantities and variance of xi is sigma square, therefore independent of any other variables. Thus, we have the unknown quantities alpha, beta, sigma together with the density functions f1, f2 and fn. Then the vector of unknowns involve both real valued and abstract valued quantities. Therefore, by definition, the setup is semi-parametric. Next, come to the setup of our main interest. The setup is non-parametric if the vector of unknowns is completely abstract valued. For an example, consider n IID observations from an unknown distribution function fx, where the functional form of f is unknown but known to be continuous. Then theta equal to f, that is theta is unknown and totally abstract valued. Therefore, omega, the space of theta, is the class of all absolutely continuous distribution functions. Therefore, the setup is non-parametric. Let us consider another example with two samples. Suppose xi, I from 1 to m, and yj, j running from 1 to small n are two samples where xi are IID observations from an unknown density fx, yj are IID observations from an unknown density gx, where f and g are both unknown but known to be continuous. Then theta, the unknown quantity, contains f and g as its elements. Therefore, theta is unknown and abstract valued. Thus, this again gives a non-parametric setup. However, before the construction of any inferential problem, we must characterize the unknown quantities. So, we start with the concept of a functional. The unknown quantity of interest is defined in terms of a functional under a non-parametric scenario. Actually, a functional is the non-parametric analog of a parametric function of parametric setup. For specification, suppose script f is the class of all absolutely continuous distribution functions. Then a functional is defined by a real valued function defined for every f belonging to the class of distribution functions. Then theta f is a mapping from the abstract space to real line. In non-parametric inference, the objective is to learn the value of theta f for a known functional theta based on IID observations from an unknown distribution function f. Thus, a functional is very like a function of unknown distribution function f. let us explain the concept through some examples. Assume xi are IID observations from an unknown distribution f, where f is as usual unknown but known to be continuous. Then few possible functionals are: number 1, theta equal to expected value of indicator x less than equal to a, where a is known, under capital F. As our next example, we consider the expected value of x, where the class script f contains all distribution functions with finite expectation. As our last example, we consider expected value of x square, where naturally the class contains all distribution functions with finite second order moments. A functional can be either linear or nonlinear. We start with linear functionals. So we start with the definition of a linear functional. Consider two distribution functions f1 and f2. Then any linear convex combination of them is also a distribution function. So if alpha is a positive quantity lying between 0 and 1, then for such a alpha into f1 plus 1 minus alpha into f2 is also a distribution function. Suppose we calculate functionals theta f1 and theta f2, and the functional based on the combination distribution function alpha f1 plus 1 minus alpha f2. If the latter functional is again a linear convex combination of theta f1 and theta f2 with the same set of weights, the functional is linear. So mathematically, if theta alpha f1 plus 1 minus alpha f2 is equal to alpha theta f1 plus 1 minus alpha theta f2, then the functional theta is linear. Then it is easy to observe that the functionals already discussed in examples are linear functionals. For example, in example 2 and example 3, we have discussed expectation of x and expectation of x square. So each of the functionals can be expressed as expectation of psi x for some function psi. Naturally, for example 2, psi is x, and for example 3, psi is x square. As another example, in 1, we have considered probability x less than equal to a with known a. So here psi x is nothing but the indicator function of x less than equal to a. Since expectation of an indicator function is nothing but the probability x less than equal to a, so here psi x is indicator x less than equal to a. And for all these functionals, theta alpha f1 plus 1 minus alpha f2 equals alpha theta f1 plus 1 minus alpha theta f2 for every 0 less than alpha less than 1. Therefore, the above functionals are called linear functionals. We have already seen that functionals can be linear. However, there can be nonlinear functionals as well. The idea is the same as before. If the equality doesn't hold after considering the linear convex combination, the functional is defined as linear. So, there can be nonlinear functionals also. The idea is the same as before. If the equality doesn't hold after considering the linear convex combination, the functional is defined as nonlinear. So, if we calculate functionals theta f1 and theta f2 corresponding to two distribution functions f1 and f2, and consider a linear convex combination alpha f1 plus 1 minus alpha f2, where alpha is a quantity lying between 0 and 1. Then naturally this new combination is also a distribution function. So if we calculate the functional considering this distribution function, then if theta based on alpha f1 plus 1 minus alpha f2 is not equal to alpha into theta f1 plus 1 minus alpha into theta f2 for every alpha, then the functional theta is called nonlinear. Now we shall consider some examples of nonlinear functionals. For example, expected value of x and its square. So we get the square of the expected value. This is also a functional but is nonlinear. Another functional of interest is the variance of x. Really, this variance of x is also a nonlinear functional. So how to check whether a functional is linear or nonlinear? So we consider a related example. Suppose x1, x2, xn are IID observations from some distribution function f, and our functional of interest is the square of the expected value. Suppose script f is the class of all absolutely continuous distribution functions but with finite expectation. Now take two fi, that is f1 and f2 belonging to this class. Then for any alpha belonging to 0, 1, alpha f1 plus 1 minus alpha f2 is again a distribution function, and if we evaluate expected value of x under this distribution function, we find that expected value of x under the combination distribution function is nothing but the combination of expected values of x under f1 and f2. It is quite evident that this will happen because expectation of x is a linear functional. But what about its square? So we find that expected value of x under alpha f1 plus 1 minus alpha f2, the square is not equal to alpha of expected value of x under f1 square plus 1 minus alpha expected value of x under f2's square. Therefore, by definition, theta is not a linear functional. Now, consider some other types of functionals. Suppose xi are IID observations from an unknown distribution function fx, where f is unknown but known to be continuous. Then f inverse half, that is the median, where script f is the class of all absolutely continuous distribution functions, is also a nonlinear functional. If we consider the quartile deviation, then the functional will also be a nonlinear functional. So now we introduce the concept of a plug-in estimator. We have discussed analogues of parametric functions. Now we need an analog of a statistic. Plug-in estimators are the required analogues. Consider n IID observations from an unknown distribution function capital F. Suppose capital Fn is the empirical cumulative distribution function based on the data. Thus, you can recall that Fnx is nothing but the proportion of observations less than equal to small x, where small x is a known quantity. So, if theta f is the functional of interest, then theta fn is the plug-in estimator corresponding to the functional theta f. That is, fn is plugged into the place of f in the expression of theta f. Now, consider some examples of plug-in estimators. Suppose xi are IID observations and Fn is the empirical distribution function based on the sample. Therefore, theta Fn is the plug-in estimator corresponding to the functional theta f. Therefore, expected value of psi x under Fn is the plug-in estimator corresponding to the functional expected value of psi x, and this expected value of psi x under Fn is nothing but the arithmetic mean based on psi xi values. As another example, we can think of Fn inverse half, that is, the sample median is also the plug-in estimator corresponding to the population median. However, be cautious while defining functionals. We explain through an example. Consider the class of all absolutely continuous distribution functions with symmetry at the origin. Then, what will be the type of the functional probability x greater than 0? At a first look, it appears that it is a linear functional, but symmetry at the origin gives theta f equal to half. Therefore, theta f is not a functional, though it looks very much like a functional. Thus, we have seen the difference between different inferential setups. We have introduced the concept of functionals as an analog of parametric functions. We have plug-in estimators as an analog of statistic. And all these concepts are supported by a number of examples. In the next module, we shall discuss U-statistic, define U-statistic in the context of non-parametric estimation.